Oh, that's because the grad school set up the Zoom. I normally set up my meetings to record automatically. Okay. So let me just recap that for the sake of the video. So in the chamber data set, what we saw was when we did the distribution for the difference in the outside and inside, in this situation, we saw that there were some rather extreme values on the difference scale. And that meant that when we tested whether the mean was 0 or not, we got very different answers for the parametric test and the non-parametric test. It was significant only at 11% in the t-test and 1% in the non-parametric test. And what we saw was if we looked at the log ratio of outside to inside, so here we're implicitly testing whether the ratio is 1 or not, rather than whether the difference is 0. And in this situation, we now get a very different answer, even though on the face of it, this seems like a very similar question, right? A log ratio of 1, a ratio of 1 or a log ratio of 0, you would expect the answers to be similar to testing whether the difference is 0. But in fact, you can see here on the log ratio scale, it's very strongly significant whether we use the parametric or the non-parametric test. So in fact, there's one more thing that we could do, is to think about the non-parametric test. Now, actually, there is a slight question here about the ranking. So I said to you that the non-parametric test is like a test on the ranks. It's like doing the t-test on the ranks. But in this case, the question is, are we looking at the ranks of the original data or the ranks of the difference? So let me just show you what happens if we look at the rank of the difference. Now, in JMP, there's actually a very easy way to create a variable that's the rank of the difference. So if we have done the distribution of the difference, one of the things we can save is the ranks. Now, it gives us two versions of ranks, ranks and ranks averaged. So we need to explain the difference in these two. So the example is, imagine that we were dealing with the Olympics, or indeed any race, right? So say it's the 100 meters. And two people come in equal first in the 100-meter race. So what medal do you give to those two people who come in first? So the difference here is essentially, if you think about in the Olympics in practice, if two people come in first, they give them both a gold medal. And then the person who comes in next gets the bronze medal. Basically, nobody gets the silver medal. Right? So actually, if you think about it in a rank term, that's a bit odd. All right? So in rank terms, what we're saying is either you should randomly give people the gold and the silver amongst the first two, or they both share the gold and the silver. So in other words, instead of giving them both rank 1, we would say one came first, one came second, they should get an average rank of 1.5. Or we randomly allocate ranks 1 and 2. So when we choose ranks here, that would mean we will randomly allocate ranks amongst those where there's a tie. Ranks average says all the ones in the tie, we add up their ranks and give them all the same average value. So ranks average is generally a much more appropriate idea in statistical terms, because we don't know, if you like, who should have got first and who should have got second if they came in the same time. So if we use rank difference, then you'll see now we have this new variable, rank average difference. So rank average difference of 1 is the largest negative difference, and rank average 24 is the largest positive difference. So if we now look at this. Well, actually, we don't know quite how to test the rank average difference. So we can't do that way, because the real question is the average difference 0? We can't test that once we've got the ranks. But what we could do instead, so I'm going to delete this column, we could have ranked the data outside and inside separately, and then ask the question whether the difference in the ranks is 0. Okay, so what I'm going to do now is look at the distribution of outside and inside. And for each of these, I'm going to save the average rank. So I now have the rank for outside and the rank for inside. I can now look at the difference between these two and see what that looks like, right? Because if average and outside, there is no difference between them, then the ranking should also show no difference, right? So we can look at the difference in the ranks and see whether that is on average 0. Okay, so we can do something, but in this particular case, it's a little bit more tricky to use the ranks in order to find the non-parametric version. Okay, that's enough on that data set. I'm not going to save that. So my next data set to look at is called height weight 15. So please open the one called height weight 15. So I'm still losing my window off the screen. Let's see, can I force it back onto the screen again? Let me shit. Let's see whether I can see it now. No, I still can't. It's lost my JMP window off the screen, so I'm going to have to come back to here. So height weight 15, so it's HTWT 15. So this data set has the height and the weight of 15-year-old children. This is an American data set, so they still live in the dark ages. The height is in inches and the weight is in pounds. Okay, so what's the research question here? The research question is whether the males and females are similar. So we could either look at the height or the weight. So I've actually not said which it is. So let's look at this. We've got the height and the weight. So if we look at the distribution, we can first of all look at height and weight. Sorry, I'm going to reset my JMP preferences. Where are we? Oh, I can't do it right now. Where are we? I don't know how I have to reset it. Okay, anyway, this is the height and the weight. So this is all the 15-year-olds together. We can also ask JMP to show it to us classified by gender. So we can put gender in the by box here. This will now show us the distribution separately for gender equals female. And then down here below, I've got gender equals male. All right, so I'm I've got separately here. Now, this may or may not be what we want. This means we can't easily do the comparison, right? Because they're in separate analyses. So we're showing the distribution separately. It doesn't let us do the direct comparison. So that's why we may actually prefer to do fit y by x. And here, if we do height and weight by gender, then it shows us the distribution separately for male and female, but on the same graph. All right, so here we can see the comparison. This is just showing us, in effect, the plot of the data. What we want to do is to say means, analysis, of variance, and pooled t-test. So we can see here, so it now gives us a graphical representation for the males and females, as well as giving us the analysis of variance. Now, pooled t-test. Why is it the pooled t-test? Because in analysis of variance, the standard analysis of variance assumes that the variability is the same within the different groups, right? So it's pooled in a sense. So you'll see it actually says on the output here, assuming equal variances, right? So we don't have to do that. We can say unequal variances. So unequal variances, then it will add in a test of whether the variances are indeed equal. And it also shows us the result from the analysis of variance if we do not assume equal standard deviations. So I would argue it's much more sensible in general not to assume the standard deviations are equal unless you need to. Right? Because in general, in most situations, we don't really know whether that's the case. And you'll see here, for example, this is the height by gender. The overall analysis of variance result is the same as the pooled t-test, 0.02%. It tells us that for the females, the mean is about 62. For the males, it's about 66. And in fact, the test without assuming equal variance is also significant. In fact, even more strongly significant at 0.01%. Similarly, for weight by gender, the test assuming equal variances is significant at 0.03%, so not so strong. Again, we can say, I don't know whether it's equal variance or not. And then the significance level changes to about 4%. So in general, it's slightly less sensitive if we don't assume equal variances. Now, in both of these, we could also say, well, I'm not sure whether the normality is appropriate. So the non-parametric test, there are a number of possibilities. The Wilcoxon test is essentially the same as doing the paired t-test on the rats, okay? So the Wilcoxon test tells us, again, we're quite sure that the heights are different by gender. It's significant at 0.02%, right? So we're quite sure that indeed that they are different. And for the weight, again, if we ask for the Wilcoxon test, you'll see the result is almost exactly the same as the Welch's test, assuming the variances are not equal. It's still about 4%, right? So we've only got weak evidence that the weights are different, but fairly strong evidence that the heights are different. Okay, so these are 15-year-olds. There's also a 12-year-old data set here where the story is a little different. So by 15-year-olds, normally both the males and the female students have gone through puberty and are going through the growth spurts, at least have started. Okay, so before the growth spurt, the difference, or rather that girls go through the growth spurt on average sooner than boys. So we don't have such a big difference in height if we look at the 12-year-olds. Okay, so again, actually, we could argue that height and weight are multiplicative things. We could again try this using the log scale. So the log scale, or we could do the non-parametric. So non-parametric is very easy. We can look at height and weight distribution and ask to save the ranks averaged, and similarly save the ranks averaged for the weight. So here the question is the average rank the same for male and female, right? So in other words, it's basically saying we've put all the boys together and girls together and worked out their ranks. And what we're essentially saying is there any pattern that the girls tend to be lower down the list or higher up the list than the boys? So we don't actually have the measurements anymore. All we have is their ordering in the list. So let's have a look at this. Do we get a similar result? So we're going to look at the rank averaged height and weight by gender. So again, we can try the standard pool t-test. We can take away the equal variance assumption, and we can do the Wilcoxon test. And you will see now that the, again, we already knew that there was a clear difference in height by gender. So you'll see now the pool t-test is even more significant when we do it on the rank scale. And we get a very similar answer for the non-parametric and the parametric test, because the non-parametric test here is essentially the same as what we've done manually by doing the rank, taking the ranks first. So the Wilcoxon-Kruskal-Wallis test is the rank sums. So it's basically saying, is the average rank the same for the male and female? So if you look back up here, where are we? Let's look at the means and the standard deviations. So you will see the mean for females is 14.6 and for males is 28.6. So that's the average rank. And that's exactly the same as the score means in the Wilcoxon test. So by doing the rank transformation, we're essentially now asking the same question in the Wilcoxon test as we're asking in the t-test, right? So because we're asking the average rank, whether the average rank is different for males and females. Okay, and we could do the same. Oh, let's do the weight one as well. If we do the weight one as well, again, you will see that the Wilcoxon test is essentially the same. So you'll see that the significance level in the F-test or t-test is about 4%. And again, the non-parametric one is also about 4%. And the mean for female is 17 and for male is 24.6. So it's essentially exactly the same mean in our non-parametric test, where we're looking at the average rank, as we have in the t-test. Yeah, so essentially in the rank test, on the rank scale, the variances are the same, right? They're assumed to be the same. So because we've basically ranked them all from the same distribution. So we don't need to worry about the pooling or not in the case of the rank test. So, but actually, again, it's not going to make much difference, because on the rank scale, the distribution is uniform, right? If you think about the ranks, if this is really at random, then the distribution of ranks should be the same uniform distribution for males and for females. Okay. Right, so it's relatively easy then to do the non-parametric. In this case, because JMP offers the non-parametric, we might as well just let JMP do the work for us. But as we'll see later on, there are some other situations where the non-parametric test may not easily be available, and we can generally approximate that by doing the rank transformation of the data. Whoops, I've closed my Zoom window, sorry. I've lost my chat window. Okay. Somebody's reminded me, yeah. Let me turn my, yeah, I've lost my distribution thing here. Oh yes, platforms and then, yeah, distributions. Yeah, that's right, thank you. Let me turn my histograms back on again. Histogram default on. Yeah. Okay. So we have looked at the weight data. So the next one is an example of both analysis of variance and analysis of covariance. So I don't generally use the phrase analysis of covariance. If you look in the course book, I use the phrase general linear model. So general linear model meaning a linear model which includes both factors, which is what analysis of variance is, and covariates, which is what regression is. So this is the combination of regression and analysis of variance models, meaning that on the right-hand side of our model, we might have both factors and covariates, and indeed we can have the interaction between those two. So I want you to open the drug data file, the drug data set. So the drug data set is a randomized controlled trial testing what appears to be 3 drugs here. However, actually one of these 3 drugs is the placebo. So let's just have a look. So if we look at the distribution of drug, you'll see we have 10 each of these 3 drugs. Now, in fact, F is the placebo. So we're not necessarily interested in all the comparisons directly. So the first question, of course, is going to be whether there's any evidence that the drugs are different, right? And if they are different, then the question is, which drug, if any, is better than the placebo, right? So we have here, so let's ignore Y for the moment. Let's just look at, ignore X. Let's look at Y. So Y is our outcome variable after the treatment. So you'll see, in fact, the distribution of Y is quite asymmetrical. But because we have 0 values, clearly we can't do a log transform. We could do a rank transform, right? So let's just consider doing that now while we're looking at the distribution. So we are going to save the ranks averaged for the drug values, okay? So now we're going to do fit Y by X. The question is whether Y varies according to which drug was given. So again, this is our initial plot. We want to do the analysis of variance as our start point. So if we do the analysis of variance, so this, remember, is implicitly assuming that the variances are equal in the standard analysis of variance. It says standard error uses a pooled estimate of error variance. So that's why the standard error here is the same in each of our three groups, which are the same size. It says this is significant at about 3%. We can check whether it makes a difference of unequal variance. In fact, if we use the Welch test, it's now the significance level increases to about 5%, just above 5%. So for people who are obsessed with a 5% significance level, this is a bad thing. But actually, the difference is not that great. It's basically just saying, if we cannot assume that the variances are the same, then obviously, in general, our evidence is a little bit weaker. But you'll notice there is actually no evidence that the variances are different. Okay, so what happens if we do the same analysis, but this time we use the ranks of the y's instead of the original values? So if we look at this and do the analysis of variance, the answer is actually quite similar. We get it significant at about 4%. And again, we could have done this using the non-parametric Wilcoxon test. And you'll see the non-parametric Wilcoxon test is almost the same answer as doing the analysis of variance on the ranks. So in both cases, you can see our conclusion is that the significance level is somewhere around 5%, depending on the exact set of assumptions we're going to make, whether we assume it's equal variance on the original scale or we do the non-parametric test. And if we look at this, though, we might say, well, but what I actually care about is not particularly whether they're all three different. I really want to know whether drugs A and D are better than the placebo. So smaller values are good here. So if you look at the graphic, it looks like the two drugs, A and D, are actually quite similar compared to the placebo. So let's think about it for a moment. We actually want to do comparisons. We want to compare the means. So you might say, well, I can just do all the student t-tests. If I do all the student t-tests, oh, this is on the rank one. Let me go back and do it on the y values to start with. So if we did the comparison of these means using a student t-test, then it would tell us down here, A seems to be better than the placebo, D seems to be better than placebo, but there's no evidence that A and D are different. And it says they're significant at about 1.5% and 3%. But this is actually not an appropriate analysis. Why? Because now we're doing 3 tests, not 1. So saying relative to a significance level of 5%, the more tests we do, the more likely we'll get something significant. Now, in this case, we only have 3 groups, but imagine that we had 100 groups. So if we had 100 groups, even if there wasn't a difference between them, then just by chance, we would expect to find 5 of those 100 differences significant if we're testing at 5%. So what we should be doing is using all pairs Tukey's HSD. So I love Tukey's naming. He always had wonderful names for the things he came up with. So HSD stands for honestly significant difference. So it's basically saying we need to account for the fact that we're doing multiple tests. So in fact, if you do the multiple tests, this says drug A is significant at 5%, D is not significantly better than the placebo, because both of these, after we take into account that we're doing 3 tests and not 1, the significance level obviously goes up, the observed significance level. Now, There is another way of thinking about this, and that is to say, actually, what we care about here is, in many cases, not particularly whether drug A is better than placebo or D is better than placebo, but are either A or D better than placebo? Because when I look at this graph, it looks to me like actually A and D are very similar. So if in fact A and D were just two drug companies' versions of the same drug, arguably what I really care about is, does an intervention drug work relative to the placebo? So that's a slightly different question. So in JMP, we need to use the fit model in order to answer that sort of question. So the fit model is the general linear model framework rather than analysis of variance. But for now, we're just going to test, does Y depend on the drug? If we use this framework, you'll see that up here on the right-hand side, it shows us again the mean values for the three different drug treatments. And we can ask a different question. So the question I want to ask is, if I randomly allocate between A and D, do those patients do better than the ones who got the placebo? So if we click on the triangle for drug, we have what's called LS means contrast. So this says runs a customized test contrasting different levels of an effect. So I want to know whether the average of A and D, so I'm going to click both of those plus, contrast to the placebo, which I click a minus. So this now says my contrast is testing, is the average value of A and D different to the value of X? All right, so again, so basically I'm now comparing the 20 individuals who had a treatment of A or D against the 10 individuals who had the placebo. So this tells me actually I have reasonably good evidence. So it's now significant at 1%. Because now instead of comparing three groups of size 10, the power increases because I'm comparing a bigger group of 20 against my group of 10. So I might say, well, actually, I don't know. I can't tell the difference between A and D, but what I can tell is it looks like the two groups who had the active drug did actually do better than the placebo. So at least it suggests, if I really want to know whether A is better than D, I would need a much bigger study. But this study may be seen as sufficient to tell me that the active drugs work better than the placebo. Okay? Now, we can again repeat this for the ranks and we'll get a very similar answer. What we're going to do though now is to ask a somewhat different question. So what I said was we had this other variable X. So what is X? Well, X is actually the baseline measurement of Y, where Y is the measurement after treatment and X is the measurement before. So we can look at this as a different question, which is to say, should we be perhaps looking at the change in outcome after treatment? And we can approach that in two ways. One way would be to create a new variable, which is the change. Or the other way is to say we can include in our model the baseline measurement. So let's try including X in our baseline measurement. And in this situation, we can actually consider an even broader question. In addition to including the drug and the baseline measurement, we can also add in the interaction. So we click on drug and on X and click cross, then JMP includes the X star drug term. So what does this mean? So drug means, is there a difference in the outcome depending on whether I have the drug or not. X means, is there a linear effect of the baseline measurement on the outcome? And X star drug means is, does the outcome depend on the combination? So somebody asked, why is placebo -1? It's because I want to compare the average of the two drugs, which is 0.5 times A plus 0.5 times D, which is just D plus A over 2, against the placebo, right? I'm testing the difference between the average of A and D against the placebo, right? So that's the contrast, whether indeed the average of the two drug treatments is different from the placebo effect. Okay, so if I fit this model, you will see JMP actually gives me a nice graphical representation of my model. It's showing me the line of fit for the three treatments. So the X effect is assuming a common slope. The drug effect is essentially a common intercept. X times drug means the slopes are different. Okay, so the question is then, what do I get in my F test, in my model? So if we come down to the effect test, it tells me there doesn't appear to be any evidence of an interaction, first of all, right? The observed significance level is about 56%. So it doesn't appear that I need to allow for the possibility of an interaction. It tells me that the baseline measurement is very strongly significant. So there are so the outcome depends very much on how sick you were at the beginning, which is not too surprising, right? But it also seems to, you might say this, well, this says the drug is not significant. Well, I cannot conclude that because I've already got drug in the interaction term. I would need to remove the interaction term before telling whether drug and X, just a pair of them, are useful. So if we redo fit model, again, we put drug and X in there, but we don't put the interaction effect. How does this compare? So if we compare the effect test here, I need to move it up my screen a little bit so you can see this. So this tells us that the baseline measurement is very strongly significant, but it also tells us that the drug effect doesn't appear to be significant. Now, if we look at the parameter estimates on this one, you will see A and D seem to have a similar effect. So let's do a comparison. I'm going to close this one down now. I want to actually compare those two models. I want to compare the model that has just the drug term in to one that has drug and baseline in it. So we can compare like for like. So the one that didn't have the baseline measurement in, you can see that the estimated drug effect is about -2, meaning this is, remember, relative to the placebo. So it's saying there's a reduction of about 2 units in the outcome if you give either drug A or D. This is saying after we take into account the baseline measurement, actually our estimate is that there's a reduction of only about 1 unit in the drug effect. But look at the standard errors. So in the original model, without the baseline, the standard error is about 1.5. So you can see that it's not significant individually, but overall it's significant. Here, the standard error has indeed decreased. It's gone down from about 1.5 to 1, but as we saw, the estimate of the drug effect has reduced by more than the standard error has gone down. Interestingly, also look at the coefficient of the baseline is almost exactly 1. So this is suggesting to us that probably we should be asking a question about the change in the outcome variable, because this model is basically telling us y is equal to x plus a possible drug intervention effect. So indeed, we can reframe the question as the change in the outcome, because that's ultimately what we're hoping is going to happen as a result of drug. And we would assume that in the placebo group, there should be no change in the outcome. Well, actually, that assumption may not be valid. Why not? Because generally, these people are being looked after by doctors in a hospital. And so if you have been sick, let's say you had COVID and we've given you a treatment, you would expect, even if you haven't been treated, assuming you haven't died, and we have no patients who've died here, we would assume you often will get better. So let's create a new column, which is the difference, right? And so our formula is going to be y minus x. Let's apply this. So this is now telling us what is the change in outcome. So if we look at the change in the outcome, you'll see the median is -4 and the mean is -3. So this is telling us that patients are generally getting better overall. So the real question is, let's now ask the question, does this depend on the treatment? So we're going to fit the model that asks the question, does the difference change depending on which drug I got? Right, so what we would be saying is, so indeed, if we look at this, you can see the change in the placebo group is quite small. On average, there's a reduction of about 0.6 units. There is a small reduction, improvement, even in the placebo group, but it appears to be bigger differences in the two treatment groups. Again, this effect is not significant overall, but we can again look at the contrast. So the average of the two drugs compared to the placebo, right? So if we look at this, this is significant at about 4%. So arguably, we can say there is some weak statistical evidence that if we look at the change in the outcome variable from baseline to after treatment, it looks like the two treatments reduce the outcome by about 4 units compared to a reduction in the placebo of about 0.6 units. And if we just compare the two treated groups against the one placebo group, there is weak statistical evidence that this is indeed significant. So this then becomes a question for the doctor. Yes, is the last value of the nominal value by default the reference? So yes, we can change the reference category inside JMP, right? So this has been set with the placebo as the reference. We could change another one as any one of the reference, right? So in this case, we know which was the placebo after the event. So this is at the analysis stage, we know the placebo. If this is a randomized controlled trial, the doctors should have been blinded to the assignment. They shouldn't have known which treatment A, D, and F were, but at the analysis stage, we do know. So here we can see that there is some evidence that the drug treatment works if indeed a 4-unit reduction in our outcome variable is enough to be clinically significant. So again, we need to be very careful. Statistical significance just means, do we have any evidence that this is not due to chance? Whether that difference is big enough to make a difference to a patient is a completely separate question, which we are not qualified to answer. So we can go back to the doctors and say, if you think a 4-unit difference, or if you like a 3.5-unit difference by comparison to placebo, is enough to be meaningful, then it may be worth repeating this trial on a larger scale, recognizing that you will need a very large trial to distinguish between A and D, because we can see very little difference between the two intervention drugs, right? It's only 0.1 units difference between our A and D treatment effects estimated, and it's about 3.5 units different between a placebo and our 2 treatment groups. Okay, so we can see some evidence that the drugs work, but it's not compelling evidence. This could just be due to chance, but at least the fact that there's a consistent pattern between the 2 treatment groups A and D is reassuring, because quite often the biological mechanism is quite similar in different drugs being evaluated, and it does look to be evidence that treatment is better than just getting the placebo. Okay, and again, we can repeat this using the rank average, but again, this would not be meaningful this way. This suggests that actually we should perhaps look at the ranks of the differences, right? But then if we look at the ranks of the differences, then we can then ask the question whether this depends on which treatment was given. So if we look at the rank average difference and we look at the drug treatment, so here we can see that the 2 treatment groups again look very similar. They have the rank average is about 13 to 14 in the 2 treatment groups, and it's about 19 in the placebo. So we can again do the same question. Can we distinguish between these? Right, it's not significant. It's about 10% observed significance. So the evidence is still really even weaker if we cannot make that assumption that the distribution is normal, right? That the residuals are a normal distribution. And you will see the overall test here was only significant 26%. So it's not that compelling. But again, this is a small study. There's only 10 in each arm of the study, 10 in each of the allocation groups. Okay. I think we have time to do one more before we take a break. So we're going to look at something very different. This is the one called CARS. So the drug one, we had a nice randomized control trial, but sometimes the data sets we get are much more messy than that, and they're not random samples. So the fact that it's not a random sample means that we cannot talk about generalizing this to a population in the same way. So this is a data set where each row in our data set is a brand of a car in America in a particular year. So essentially, the US government tests a sample of each car model each time there is a model change. So we have a large number of makes, an even larger number of models, and they are tested each year. So this is basically safety testing, right? So what is our concern? So essentially the idea is you stick a dummy, a physical dummy in the car, and then you crash the car. So that's why you can't afford to do too many of these tests, because you're essentially probably destroying this car. And there are several different things to think about. First of all, we've got DP. DP means, is the dummy in the driver's position or in the passenger position? So these are the front seat passengers, right? So it's the driver or the front seat passenger. And then the measurements which are taken on the dummy, we have 4 measurements. First of all is the head injury criteria. So this is basically telling us how much damage is done to the head of the dummy. Chest deceleration, that's basically the force on the chest. And then this is the pressure on the left femur and the right femur. So basically you've got the damage to the legs, the damage to the chest, and the damage to the head. Okay? So in most situations, the head is the most serious issue, right? How much damage is done to the head. The chest can be quite important because, particularly for the driver, the damage might be done to the chest by you being pushed against the steering wheel. Okay? Now, we obviously can't look at all the models because there are too many different models, right? And there are only a few of the models which are measured repeatedly, and that basically means they're measured across different years. But for most of these models, they're only measured once or at most twice. So what can we say? Well, what we know about these different cars is we know what type of protection they have. We know how many doors they have. We know the weight of the car and the size. Now, the size actually isn't really the size, it's the car type. So we've got vans, we've got medium-sized cars, we've got compact cars, we've got MPVs, so we've got different types of cars. So that's actually rather messy. Now, weight is relatively simple, but it's not obvious why the weight of the car should matter that much, other than a heavier vehicle, perhaps you have to build it with a stronger body. So let's have a look primarily then at the protection. Now, the protection is a little bit tricky. So let's have a look at the distribution of protection. So here it shows us the different forms of protection. So we have passive belts, we have motorized belts, we have manual belts. D and P means driver and passenger airbags. D airbag means just the driver's airbag. Okay? So as time went by, so earlier cars, older cars just had manual belts. So that meant a seat belt that you had to adjust yourself. Now, of course, if you're the driver every day, you've probably already adjusted the seat belt to your size and shape. But if you're a passenger and you're not the same passenger every day, you may or may not have adjusted the seat belt properly. So passive belts and motorized belts are different ways of adjusting the belt to fit. And then airbags are more recent. So generally you can assume airbags means you already have a belt, but you also have airbags. So again, if you're the driver, it shouldn't matter whether you have the driver's airbag or the driver and passenger airbags. But if you're the passenger, it most certainly makes a difference, right? So we can see that the effect of these protections may not be quite the same if you're the driver or the passenger. And then we also have the difference that the driver has a steering wheel. And so one of the main forms of damage in an accident may be the steering wheel against the driver. So the passenger, in that sense, airbags arguably are not quite so important because you're not going to hit against the steering wheel. If you're wearing a seatbelt properly, unless you go all the way forward to hit the front of the car, it shouldn't be as damaging, right? So we can ask the question then, at least, can we identify driver-passenger differences and can we identify protection differences? And we can also put weight in there just to see what's going on. So let's start by fitting y by x, just to try and see how the head damage depends on driver or passenger position, the protection, and the weight of the vehicle. So we're going to look at these individually. So first of all, we're going to just look at the quick analysis of variance, or t-test. This says, indeed, there is a difference that overall drivers have more damage done to them than passengers. As I said, that's not surprising because you've got the steering wheel as an extra thing to do damage. When we look at the forms of protection, this, as I said, is a little bit more tricky. So you've got the one that has the most damage. So let's look at the pairwise comparison. So let's do all the Chuki HSD. So this tells us, if we come down here, that manual belts have the most damage. And then, so we can basically distinguish manual belts from almost everything else except driver and passenger bags. Why? Well, driver and passenger bags, we have relatively few cars. We only have 3 cars that have both driver and passenger airbags. So that's why we can't distinguish it. Clearly, driver and passenger airbags has the least damage. It's just it's a very small sample. We can see that the passive and motorized belts, the difference is relatively small. And then we can see that airbags generally is the least. Right? So we could, for example, group passive and motorized belts together. But the driver and passenger airbags versus driver airbags, it does look like the driver and passenger airbags are more protective. But again, we need to be careful because this may depend on whether you're a driver or passenger, right? If you're a driver, these airbags should give the same level of protection. Right, so overall, we're quite clear that protection does matter. And at least it looks like manual belts are the least protective, motorized and passive then next, and airbags the next. So, and then what about the weight of the car? Where did my third one go? Did I not do the third one? Oh, have I lost it over to the right? No, I didn't do it. Okay, let's try that one more time. Let's also do that. How does the head damage depend on the weight of the vehicle? So this, you can see this doesn't look particularly linear. It doesn't look like a very strong relationship. So one of the issues here is that maybe there's a scale problem. So if we look at the distribution of the head damage and the weight, you will see these are both quite skewed. So this suggests we should either do a log transformation or a rank transformation. So let's do a rank transformation because then that means we're doing at least some approximation to a non-parametric approach. You can see the weight distribution is really quite asymmetrical. So we're going to change our dependent variable to be the rank of the damage to the head and the weight. So let's now look at fit y by x on the rank scale. So now rank distribution should be approximately uniform. So now you can see this is we've basically got a much more consistent pattern here, but is there any evidence of a relationship? Doesn't appear to be much, right? So it doesn't look like the weight is going to show up anything. Now, of course, this could be because this is a very weak relationship, or it could be that it's not very linear. Oh, sorry. I should have said what we can do is we can, inside JMP, do other things as well. We don't have to assume linear. We can try a nonlinear relationship. So in fact, inside JMP, we can do fit flexible. So we're going to try fitting a spline. A spline basically means a curve where we can control how much smoothing there is done. So this slider here lets us choose a very unsmooth curve. This clearly doesn't make sense. As we increase the smoothing, you can see that maybe there is an effect here that the heaviest vehicles also have the most damage, right? So it doesn't look like heavier vehicles have less damage. If anything, maybe they have slightly more, but this is only amongst the more extreme ones, right? For this whole range here, it doesn't look like there's much of an effect. So we can include that in our model just to see, but it doesn't look to be a very strong effect. Okay, so now let's try fitting our model. So we're going to do the rank average head. We're going to include the protection. We're going to include whether it's driver and passenger. And we'll include the rank average weight just to see whether anything shows up. We add these in here together. So does it seem to show very much? Well, it says it is overall significant, but we know already that the protection matters. This says there's some weak evidence that as the weight goes up, then the damage goes up. And if we look at these here, it says indeed the driver generally has more damage than the passenger. And it says, so this is relative to, I think, the passive belts. So we could change the reference one here, but the main thing is you can see manual belts have the most damage. Motorized belts is similar to passive, and the airbags generally are better, right? Again, the protection from driver and passenger airbags looks more, but we're going to be careful because that's partly because driver airbags don't protect the passenger. So in this case, right, actually, we would expect there to be an interaction effect between driver, passenger, and protection, because the airbag doesn't protect the passenger, only protects the driver. Okay, so how much did we explain of the variability? Not a lot. We only explain about 20% of the variability in the damage. So clearly this is not a very successful model. Yeah, we are going to try the interactions now. I just want to understand how relatively good this is. So it's not great. So we can try interactions. In fact, we can try all the interactions. This is not too small a data set. So we can actually try all the two-way interactions. Three-way interactions gets a bit too complicated. So we're going to try driver, passenger, protection, and rank averaged weight. And in JMP, we can tell it, please include all the two-way interactions. This is what it calls factorial to degree. This says add the columns and the interactions to the degree, and the degree is normally 2. So this will include the main effects and the two-way interactions. Let's see how well that works. That doesn't make a big increase. So let's ignore the parameters for the moment and look at the effect tests. In fact, this suggests that the interactions with weight are not significant. So the only interaction that's significant is driver-passenger versus protection, which is the one we expect. So let's remove the other two interactions. So we're just going to put back our 3 variables: driver, passenger, protection. Well, we're going to put this plus the interaction. And then we're going to add back the rank average weight as well. So this explains about 24% adjusted R squared. And this says that all of these are significant at about 1 to 1.5%. You can see the most important thing, though, appears to be protection, not surprisingly. And the driver passenger protection, right, as I said, if we put these together, let's have a look over here. So this is telling us for the combination of driver passenger with the protection. So we can use this to try and understand what's going on. So what I said is logically, the protection for the driver should be the same for the two airbags. So it's about 92 against 100 is the mean for those two. Whereas for the passenger, it should make a big difference, and it does. So the passenger for the driver airbag is 110, whereas the passenger with driver and passenger airbags is 33. So you can see for a passenger, obviously I'm much better protected if I have a passenger airbag. So that says that quite a lot of our interaction effect is probably due to the airbags, because if we compare for the belts, so you can see that for the driver, manual belts is 232, passenger manual belts is 167. So generally, the driver is going to be less protected for the same type of airbag than the passenger, which is what we expect. If we look over here, on average, the driver has a damage of more about 50 rank more than passenger. So we could expect, in general, the driver's protection to be about 50 worse. In fact, if you look at the airbags, which are relevant, then indeed the passenger is about 50, 60 better than the driver. If we look at the passive belts, you can see, indeed, the passenger is about 50 or 60 better. Motorized belt, the driver is about 50 units better. In other words, what we should really be saying is what form of protection is relevant for you, right, rather than for the car, because it's about whether it's relative to you. So arguably, we should create a new variable which says, for a particular driver or passenger, what is your protection, right? Because the way it's being done here is by the car type. So somebody asked, can we check for overfitting? Well, there is here more than 300 observations, and we're only fitting 10 parameters. So in general, that's not going to be a major problem. We will talk about some overfitting issues later on when we come to models which are more complex. Okay, so what I'm saying here now is arguably we need to create then a new variable. So let's just think about how we might do this. So this is basically protection for the individual. Okay, and so we want to create a formula for this. So depending on whether you are the driver or the passenger, so DP, so we're going to compare, we're going to do a conditional on this. So if driver passenger, sorry, I put this in the wrong place. So if the driver passenger is comparison is equal to driver, right? So if you're equal to driver, then so and so, otherwise you're the passenger. So if you're the driver, then what do we need to do here? Well, if we need another conditional in here. So remember, we've got essentially, we argue there are essentially 3 levels of protection. manual belts, passive belts, and airbags, right? So if protection, so there is, and then for protection, we again want to do conditional, and we actually want to do conditional match. So it said match from, sorry, I did that very quickly. Let me redo that. So that was match from data. So conditional match, and then when you choose match, it lets you choose match from data. So it's automatically inserted in here for me the 5 different possible values of protection. So we can remove this one. So if it's driver's airbag, then the protection is airbag, right? If it is driver and passenger airbag, then again, it's also airbag. Manual belts is manual belts. If it is motorized or passive, we said this is similar. So I'm going to put M/P belts because I'm going to merge these two together because there seemed to be no evidence they were different. So I don't need this then clause. I want it like this. So I want if the driver passenger is the driver, then if it's a driver airbag, that's airbag protection. If it's driver and passenger airbags, that's airbag. If it's manual belts, it's manual belts. Motorized or passive is MP belts. That's all my combinations, right? Yes. Have I got that right? Yeah. So I can remove this clause as well. Let's delete that. Right. So for a driver, these are my possibilities, right? And this is the level of protection for me as an individual. So what I'm going to do now is select this match protection set. I'm going to copy that and paste it in here. So I'm now starting out with the same answers for passengers as drivers. That's not quite correct, because if it's a driver airbag, then actually I don't have airbag protection. And in fact, this is it's external knowledge. As I said, it went through the stages of manual, motorized and passive, and then airbag. So actually a driver airbag only normally means that the passenger has got MP belts, right? Either motorized or passive. So I'm going to change this one to be MP belt. So this is based on some external knowledge about the sequence in which cars change. So a car that has a driver airbag normally would have motorized or passive belts for the passenger. Okay? So you can see that all we've essentially done is changed the airbag protection to be whether or not this individual has in this position, has that protection. Okay? So let's see if I've got that right. If I've done it correctly. Protection for individual. So I can check that quickly by looking at protection for individual against driver passenger. So we've got no missing data, so at least that part's correct. That's not really sufficient, is it? I can at least check protection for individual against protection. So this should match except for the driver airbags, right? So you'll see that the driver airbags, 30 of them are airbag and 30 of them are now MP belts. All the others we have matched. Driver and passenger airbag is airbag, manual belts is manual belts, motorized belts is MP belts, passive is MP belts. Okay, so it looks like I've done my coding correctly. So we can now do the comparison. So we had the model which had that the head damage depends on the weight and the driver protection, passenger protection, and protection. So this one, I had an adjusted R squared of about 24%. Remember, this is what this was our table looked like. So this is the one without interaction between the two. Sorry, I should do the one. Let's compare the one with interaction. So damage to the head, driver, passenger, and protection, plus the rank average weight. So I can compare this one to my new one, where I believe I don't need the interaction because I'm going to use the protection for the individual as well as the rank average weight. So we're going to compare these two models. So the adjusted R squared, whoops, what did I do wrong? Oh, sorry, I forgot the driver passenger variable. Try one more time. So rank average head, I want driver protection, passenger plus the protection for the individual, plus the rank average weight. Okay, but I don't need the interaction term, I believe. So indeed, you will see the adjusted R squared for this model is higher than the one with the interaction. So I've gone from 24% adjusted R squared to 25%. That's still not great, but that's because this model now only has 4 parameters instead of 10. And the sum of squares for the model has only gone down a little bit. So this model says, now, if I look at this, this is saying driver versus passenger. So the drivers generally have about 65 units more damage than passengers. And this is saying very clearly now, manual belts are the worst. The damage is around 200 on average, taking into account both driver and passenger. I get about 50 units of protection by switching to motorized or passive belts, and about another 90 units of protection by switching to an airbag. So this shows very clearly how strong the effect is, and you will see all of these effects are very strongly significant. So we can indeed see, oh, and we can do the, yeah, so this is comparing the airbags and the MP belts against the manual belts. Is that right? Where are we? Protection for individual. Yeah, yeah. So we can see definitely you're better off having the manual protection belts than manual, sorry, motorized belts than manual, and airbags than motorized belts. Okay, so let's take a break for a few minutes. I'm sorry I went longer. I meant to give you a break before now. Let's take a 10-minute break or so, and we'll restart at 11:30. Okay. If anybody has any questions, you can ask me now, either through everyone in chat or directly to me in chat. Okay. Okay, so we have got through the first 6 data sets. Now we're going to move on to one that I like very much. Is called growth. So this is a very simple data set, but it's a very nice one to illustrate some of the things we want to look at. Okay, so this data set has just 2 measurements. The 2 variables are the age of some babies and the ratio of 2 measurements of these babies. So the 2 measurements are if I remember correctly, the circumference of the head and the length of the baby. So you've basically got a shape, if you like, of the baby's body. So let's just look at plotting the data. So we're going to plot ratio against age. And we get a graph that looks like this. So when you see a graph like this, the question is, what exactly is the research question? So the research question is arguably, can we predict ratio well based on age? Okay. So if I ask you the question, do you think we can predict ratio well if we know the age? So what's your answer to that? Do you think we should be able to predict well? Yes, we should be able to predict quite well, right? Because we can see the variability for a given age is relatively small. So now the next question is, do you think a linear model would fit well to this data set? Right? Do you think a linear model fits well to this data set? No? Well, let's have a look then. Let's ask JMP the question. So within this graph, we can say fit line. And so if we look at the answer to fit line, the adjusted R squared is 82%, and the F test, or the T test for that linear model, is significant at less than 0.01%. So if you were given this data set and you did not plot it, you simply put it into a regression package or a regression calculator without ever looking at the data, you probably would think this is quite good already. And you might well be willing to accept a linear model, even though once you've plotted the data, it's very clear that a linear model is not sufficient. So if instead of using the fit y by x, we use the fit model. So let's do it within here, because then we have more tools to evaluate it. So now if we can see, indeed, the regression plot shows that this is not very good. And if we look at the residual versus predicted plot down here, you can see very clearly there is a strong pattern when we plot the residuals. So in general, plotting the residuals is a very important thing to do as a matter of course. We should regularly check the residuals. So for example, by plotting them against the predicted values to see if there's a pattern. So the sorts of patterns we're looking at include whether there is, like here, a general pattern as the predicted values change, the average value of the residual changes. The other thing we need to be aware of is we are assuming in a standard linear model that the variability is constant. So we're also looking for evidence that the variability changes. And indeed, the variability is quite different here from this part here. Now, in terms of what to do next, there are several different approaches. So if you come back and look at the original data, there is at least 3 different possible thinking to this. One would be to say, well, maybe there's actually 2 stages of growth. The initial stage with a high slope, and then the second stage with a low slope. So again, actually, if we do fit y by x, there's something more we can do on this, which we can't easily do in the fit model. We can do what we were doing just before and ask JMP to fit a smooth curve to this. So if we say, rather than fitting a linear model, use the flexible fit spline, and we start with the stiff spline, which is basically then going to give us the linear relationship. If we now reduce the stiffness by moving this slider to the left, you will see that it changes and changes. If I go too far to the left, we get a very bumpy line. It doesn't make sense. So we're basically looking for a relatively smooth line that fits our data well. So you can see that relatively smooth line here does indeed suggest maybe fitting two different slopes. One slope here and another slope here. So that would be one way to think about this, where we would then have to try and work out, right, saying at age, what, maybe 15 or so, 15 to 20, we change the stage of development. And indeed, with human growth, we do know that we have different stages of development. Now, traditionally, people, rather than using spline fit, would use polynomials. So let's have a look at what happens if we try to fit polynomials. So in other words, it's quite clear from the residual plot here that a linear relationship is not sufficient. So we might say, well, what happens if we fit a quadratic model? So if we do fit polynomial quadratic, you can see, sorry, let me go back and show the fit line for comparison. So the fit line, we know is not very good because we've got all these values below the line, then all of these above, and then up here, these values below. So the quadratic does look better than linear, and it comes closer to these points down here, and it comes closer to these points here. But again, for people who don't look at the data, what conclusion would we reach? So the linear fit, the adjusted R squared was 82%, and it was significant at less than 0.1%. The quadratic one, the adjusted R squared, goes up from 82 to 87%, and the quadratic term is significant, right? So that definitely the quadratic is better than the linear. It's not immediately obvious whether that's enough to stop, but in fact, in this fit model, we can try that. We can, in the fit model, put not only age in here, we can put age crossed with age, which is age squared. And if we look at this, again, you can see the residual doesn't look very good. It's better than just the linear model, but clearly it's still not a very good residual plot. We can see there is still clearly a pattern here. So similarly here, if we now say, well, okay, let's try a cubic term. So we'll do fit polynomial cubic. So it's getting a little messy. So I'm going to take away, for the moment, the linear fit. So if we compare the quadratic and the cubic, it does seem the cubic is a little bit better down here and a little bit better up here. We can go down and look at the test. So if we look at the cubic model, the cubic term in here is very strongly significant. So in terms of statistical evidence, we'd say, yes, there's no question that the cubic model is better than quadratic. And the adjusted R squared has now gone from 87 up to 92%. So this looks better purely from a statistical evidence perspective. You might say, well, why don't we keep going? Let's go from a cubic to a quartic. So that's the fourth order. Now you'll notice that the quartic is a little bit odd, that just around the end of the data, it suddenly drops down In fact, the cubic also is a bit problematic. The cubic is suddenly going up here at the end here. And it does look like the quartic is better. So again, we're going to remove the quadratic one to try and make it easier to see what's going on. So again, you can see that the quartic does seem a bit better. What about the fit? So it says the fourth order term is very strongly significant. And we've now gone from 92 to 95%. Okay, so why don't we keep going? So if we now try a fifth order polynomial, we come down here, we can say the fifth order term is still strongly significant. The adjusted R squared has gone up to 96%. Okay, so let's remove the cubic one. So this is now the fourth and the fifth order, and you'll see the fifth order also does something strange at the end of our data set, suddenly goes up here in a very extreme way. So let's try a sixth order polynomial, which again drops down at the end. So the sixth order polynomial, now this is no longer significant, the extra term. So you might say, okay, we don't need the sixth order, but we thought the fifth order was then the best as we kept going up. And you can see that actually this is fairly close to the smooth spline within the range of the data, although the spline doesn't do something quite so strange up here at the end of the data. Okay, but the problem with this is this fifth order polynomial is a very complex model, right? So let's say that we were talking to a pediatrician. He was saying, can you please give me a good model to explain the relationship between ratio and age? It's a little hard to explain what's going on here, right? How do we explain this model? What do all these coefficients mean? That's really a little bit hard to explain. Well, so what about thinking of other ways? What about possible transformation? So we said that quite often log is useful, and ratio, by definition, a ratio after taking logs becomes the difference of two terms. So why don't we try doing a log transform? So fit special allows us to do a log transformation on the y and compare it. Actually, that doesn't look very good at all. In fact, the log transform on y is almost the same as the original scale. So neither of these are very good. So we said the linear one was only an adjusted R squared of 82%. The log transform was even worse. The adjusted R squared went down to 73%. So we don't like the simple log transform. So what else could I do? What might be better? Well, if you know something about growth, you'll know that growth is often exponential in biological processes. So an exponential growth actually means we need to do a log transform for both x and y. So log transform of y and x corresponds to y being an exponential relationship in x. So let's see how that does. So the log-log transformation looks much more reasonable. So let's go down and see how that did. And we'll see the adjusted R squared is 95%. So it's not quite as good a fit as our polynomial, but it's enormously better than the linear one. So let's remove the linear one again. So you can see these three models actually look quite similar within the range of the data. So the advantage of the log-log transform is we can interpret this biologically as being an exponential growth relationship. And the adjusted R squared is almost as good as the best one we could find with a polynomial. In fact, it's about the same as the fourth order polynomial, not quite as good as the fifth order polynomial. But this one is now very easy to explain. This just says log of the ratio is roughly minus 0.7 plus 0.16 times log of age. So 0.6 times log of age essentially means that the ratio depends on age to the power of about 1/6, right? Or if you think it the other way around, ratio to the power of 6 depends on the age, right? So we essentially have an exponential relationship between ratio and age, which explains most of the variability in our data. And if we now do the comparison of that, if we look at that, so if we're now going to do a fit model, but we can't in JMP do this directly, we need to first of all create 2 new columns. So we're going to create 2 new log columns. So my 2 new log columns. So my first one is going to be log ratio. If I do column info, I want this to be log ratio. And my formula is very simple. I'm just going to do ratio and then take log the base 10. Finding difficult to fit everything on my screen. Okay. That one should be fine. And then for log 2, I'm going to change this one using column info to be log age. And my formula is then just age transcendental log 10. So now I can then do my fit model on the log scale. So fit log ratio, depending on log age. And you can see now, although my data points are not evenly distributed, this is not too far off log model. And again, the residual plot is not perfect. This data point is a bit low, and there's maybe a little bit of curvature here. This is at least immeasurably better than the original linear model on the original scale, right? So this at least is a lot better than just doing things on the original log scale. Now, we're going to talk about different criteria for model fit. So adjusted R-squared is generally considered old school in model fits. People generally use now AIC and BIC. But one of the big advantages of adjusted R-squared is it's scale independent. So transforming Y, adjusted R-squared is still meaningful. So why did I use log 10? Is because log of both X and Y, when you do the inverse transformation, is an exponential model, right? So log Y, log Y having a linear model in log X, when you convert it back, means Y is exponential in X, okay? It's equivalent to Y is A times e to the power of X, okay? Or alternatively, you can write it as Y is proportional to X to some power, okay? So the 2 log transformations is appropriate if we think there is an exponential relationship between our variables. And as I said, that's not often going to be the case, but for growth equations, we know that biological growth is often exponential. Okay, so that's where some subject knowledge may be helpful. Okay, so that sounds like the end, but actually I want to approach this in another way. So I mentioned before that rank can be helpful when we are concerned as to whether the normality as assumption is appropriate. But there's another way of thinking about this, If we go back to the original data plot here of ratio against age, you can see that basically what's happening is that the ratio increases with age. That's the one thing we can tell from this graph, is whether or not this is really a linear model. What seems quite persuasive is as age goes up, ratio goes up. So the other way to look at this is to say, well, let's look at the rank transform of ratio and age and look at what the relationship is between them. So if you look at this, you can see the ratio is rather asymmetrical, but never mind, let's just save the rank's average values. The age, we almost don't need to do a rank transform because this is almost uniform already. But just to be comparable, I'm going to do the rank age down here. So then we've basically thrown away all the information about the exact ratio and age values. We have simply saved the information about the ordering of these babies by their ratio and the ordering of these babies by their age. Okay? So let's now plot rank averaged ratio against rank average age. And lo and behold, we have an almost perfect linear relationship. And if we now fit the linear model to this, you can see the linear model works remarkably well. And what about the adjusted R squared? That's again about 95%. So in other words, the model that says the rank of ratio increases linearly with rank of age has almost exactly the same fit as our log-log transform model in terms of how well the model fits. So in other words, that suggests that the part that isn't explained from the rank-rank model is probably genuinely random variation that has nothing to do with age. Right? So we can explain about 95% of this by simply saying, as the age goes up, the ratio goes up in a consistent way. Now, the disadvantage of this particular approach with the rank is that we no longer have the original scale. So if I say this particular data point has a rank of age of 40, I don't know what that means. So if I'm explaining this to the doctor, the pediatrician, he would say, but what age is that? But as I said, in this particular case, we could still have looked at the rank ratio against the original age, and you'll see the plot is almost exactly the same because the ages generally are uniformly distributed, right? So in this particular case, we can say the rank, right, we're generally going up in this particular form. We can suggest this is the model, but that means, again, the rank will change if you change the data set, right? So if you have a different set of children, so this is not useful for predicting the ratio, right? Except within the data set. But it's giving us the confidence that that log-log model has already explained most of what can be explained in terms of how the ratio increases with age, because the adjusted R squared is almost exactly the same as this rank model, right? So we've essentially explained how ratio increases with age. Anything beyond this is probably overfitting, because you can see that here the pattern is almost completely uniform, except the variability is less down here because we don't have many babies down here in this low age and low ratio. Okay, so that just gives us another way to approach this problem and give us the confidence that our conclusions on how ratio depends with age do not depend very much on the particular functional relationship between age and ratio. It's just generally telling us as age goes up, ratio goes up, and to a reasonable approximation, That's an exponential relationship. Okay, so next one is RO. So RO, this data set, oops, I didn't mean to close that. This data set is going to show us something quite different, something that we haven't considered yet, which is what's called leverage. So leverage has to do with not simply how important is each variable, but whether our model depends particularly on a few data points. So if you're somebody who does designed experiments, well-designed experiments, then you should not have a problem with leverage, because generally all of your data points should have similar importance in terms of the fit of your model. But there are often situations where the data set is not from a designed experiment. We either can't control everything, or for some other reason we can't do an optimal designed experiment. There may be some constraints on how we can collect the data. So please open the RO data set. So we get this one illustrates again, well, this illustrates really a different point. This illustrates that looking at the individual X variables alone can be misleading. So there are some people who have been taught that the way to analyze a data set with multiple X's is that you must look at each of the X's, decide which ones have a significant relationship with Y, and then include those ones in your bigger model. And that may be misleading. But let's look at that first. So let's look at how the yield, so the yield is our outcome variable here, and we have three different possible covariates: aperture, ranging, and cadence. So we're going to look at each of these three separately and fit a simple linear model. Okay. So when we fit the simple linear models here, what is our conclusion? Do we think that these three covariates each have a linear relationship, positive linear relationship with yield? Right, so please respond to me in the chat whether you think there is evidence that these three variables, aperture, ranging, and cadence, each have a linear relationship with yield. Yes or no? Only cadence is linear? But if you look at the overall significance level, all three of these have a very strong significant relationship. They're all significant at 0.05% or less, right? So if you look at them separately, yes, there may be collinearity. So it may be that actually there's collinearity, but actually, so collinearity is an issue we're going to come back to later on, because again, people are often taught you should not put collinear X variables into your model, and that's simply false. Just because variables are collinear does not mean that you should drop some of them. You may need all of these variables, even if they're collinear. But we're gonna come to a better example for collinearity in a minute. The key point is that we cannot know how useful these variables are together just by looking at how useful they are on their own. Now, it's true, cadence looks to be the most useful one, because generally, with the exception, possible exception of this one data point here. So the nice thing about JMP, if you put your pointer on it, it will tell you this is row 20 with cadence 28 and yield 65. So this data point doesn't seem to fit very well, but all the others seem to fit very well. So the adjusted R squared is 98% just from cadence. And if you look at the other two, they're not nearly as good. So aperture, the adjusted R squared is only 47%, ranging it's only 62%. right? So for a scientific type model, as opposed to a human model, these are not very good models, but there is no question that there is a linear relationship, at least if we look at them individually. So what we want to do now is to fit the model with all three of these in together. So we're going to change yield. We're going to put aperture, ranging, and cadence all together in as possible model effects and see how well that fits. So if we come down to look at how well that fits in the effect test, let's not look too much at everything else yet. This says, yes, aperture, ranging, and cadence are all very strongly significant. So it's not that they're not all useful. They truly are all useful. However, look at the estimate of the slope, and you will see something odd. Cadence, yes, it's positive, but aperture and ranging have negative coefficients. So if we come back up here, the leverage plot. So this is telling us that actually only cadence has a positive linear relationship with yield when we put these three together. That actually as the aperture and ranging goes up, the yield goes down, right? So that's rather worrying. So indeed, the adjusted R-squared is much better. It's 99.6%. But it's rather worrying. How can we have the situation that we've reversed our conclusions about the effect of aperture and ranging with cadence? Now, this leverage plot here is warning us that one of our data points, row 20, has a very high leverage, meaning our conclusion about cadence depends very much on this particular data point. Similarly, although not quite to such the same extent, again, row 20 affects the ranging. And this says row 20 affects the leverage. So in other words, our fitted model depends quite heavily on one of our data points. Now, again, some students have been taught in other courses, okay, then we should simply remove point 20 and fit the model without it. So indeed, the nice thing in JMP is that we can exclude a data point from our analysis very easily. So how are we going to do this? So if I bring up my lasso, I can lasso that particular data point. Sorry, I've lost my lasso. If I take my lasso, I can lasso data point 20. So you'll see it's highlighted in all my windows. So I can see that's actually the one that didn't fit cadence very well, didn't fit ranging particularly well, and it didn't fit aperture particularly well. If I go to my rows, I can exclude it or hide it. So I'm going to exclude this data point. I'm not going to hide it. So exclude means if I redo my analysis, it will not be included. So I'm again going to fit the model, yield, depending on aperture, ranging, and cadence. And if I come down to look at this, so the effect test still shows that aperture, ranging, and cadence are strongly significant. However, let's compare the parameter estimates. So with all the data points, I got aperture had a coefficient of -0.7. Without that data point, the coefficient is 1.3. Here, ranging coefficient -0.6. Here, the coefficient is 1.4. So I've changed, this changes my model from one where cadence is positive, aperture and ranging are negative, to where all three are positive. So that one data point has a radical effect on my fitted model, right? So this says these were significant at 0.01%, but removing that one data point flips those completely. So that's rather disturbing, right? That one data point has such a big effect. So how can we understand this? So we're going to do something different. We're going to ask the question, what is going on that's so strange with row 20? So I'm going to unexclude it. So if we do rows, exclude, unexclude, the red stop sign goes away and it's back in our data set. But what I want to do now is we're going to do a 3D plot. So I want to do scatter plot 3D. And I'm not interested in yield for the moment. I'm just interested in my 3 covariates. Okay, so I'm going to select aperture, ranging, and cadence. Now, my 3D plot is showing me all my plots in the 3D space. And if I click on here with my mouse and drag, I can rotate that space in any way I want. So I'm looking at all the different 2D projections of my data. Now I'm actually going to, first of all, select all my data points. So I'm going to, if I go back to my spreadsheet here, at the moment, I've only got row 20 selected. I want to select all rows. So that means they will all be highlighted in my plot. So for the moment, I want to highlight them all. Now, what am I trying to do here? I'm going to rotate this, looking for a pattern. So can I find a pattern? So I want you to try rotating in 3D space to see if you can find an interesting pattern. So to me, this is an interesting pattern. So why is this an interesting pattern? It's an interesting pattern because all of my data points are in a straight line except this one data point here. And if I again lasso this data point, hey, what's going on here? I want my lasso. Come on, JMP. I don't want that. I want my lasso. Okay, let's go back to my pointer. This data point here, which my JMP doesn't want to lasso, as it should. That's weird. Anyway, this data point here is my point 20 again. So this data point here, the only one which is not in a straight line in this particular view is my 20th data point. Right? So this data point 20 is different to all the other data points. So what does this mean? It means essentially whoever designed this experiment did a terrible job. Right? Why did they do a terrible job? Because although I have 3 covariates, this is telling me that actually I didn't distribute my data points well in the 3D space, right? So if you've looked at the chapter in my book on experimental design, it says we should put data points as far as possible in all of the extremes and all of the combinations of the extremes. So this is telling us actually, although we have 3 covariates, actually all my data points except for this one all fit in a 2D space. So I have very poor coverage of my space of possible values. So this data point is the only one that tells me what happens if I vary things in this dimension. Right, so this dimension perpendicular to where all my other points are, this is my only data point that gives me information about that. So this data point actually is extremely useful. So the only problem is, because I only have one data point, I don't know for sure whether I can trust the information in this dimension, because I'm reliant entirely on that one data point. So in examples like this, Right? Again, students have been told you've got a data point that's very different to all the others. It's an outlier, you should exclude it. But in this case, this data point is the most useful data point in the whole experiment. The only thing is, can we trust it? So are we sure that this data point really, there is no error in either the X variables or the Y variable? And essentially, this is telling you we need more data points in this dimension. You need to go back and collect some more data to check, because this is telling you, this data point is warning you that your conclusions are not robust because you have too little information in this direction. And if you include this data point in, or more data points in this direction, you may reach a very different conclusion about how your 3 variables predict, right? But this data point, if you include it, tells you that the other 2 variables have a negative effect on yield, not positive, right? So we have so little, if you take this one away, there's so little variability in this other dimension that we really cannot draw good conclusions, trustworthy conclusions, right? So there is in some sense collinearity, but you can see it's collinearity once you remove this data point. So once you remove this data point, all our remaining data points fit within this 2D plane rather than 3D. Okay? So how do we identify that something like this is the case? Well, you remember in our fit model, the crucial thing was this extra thing here called leverage. So leverage is basically telling us, does this one data point, each of these data points, how much do they affect our conclusions about this particular variable's impact? So you'll see that this data point 20, particularly for cadence, but also for aperture and ranging, is so important compared to all the other data points. So that should be a warning to you. You need to be careful that there is a data point here which has a big impact on your conclusions. So in fact, it looks a bit strange here. It seems more important to cadence than ranging and aperture. That's true because although cadence, the sign didn't change, the size of the coefficient changed by a factor of 3. So in fact, in that sense, it was even more important in terms of telling us about the effect of cadence, right? So again, in situations where you do not have a well-designed experiment, you particularly need to be careful about leverage, right? So in a well-designed experiment, the leverage should be similar for all the data points, right? But there are situations where you cannot design the experiment because there are things you cannot control, and so you end up with a constraint like this, right? Okay, I think that's about time to stop. Next time, we're going to start out with the Longley data set. So the Longley data set is our good example on collinearity. And then the Linerand one is when we're going to talk about fits with overfitting, problems with overfitting, and making sure we have good selection criteria for our models. And then we're going to illustrate those with the body measurements and the decathlon. The animals data set, if we get to it next time, will introduce random effects. We have not talked about random effects or nested effects or repeated measures. And then the spring data set, we will introduce binary and ordinal outcomes. And then the last data set in the JMP set is the passengers one in series G. So this is a time series data set. And then the other data sets from 16 onwards are ones I've given you in the additional data set in the Google Drive folder. which we'll look at some of these. We won't have time to look at all of these. We will certainly look at cherry tree and iris, and we'll see how time goes, which of the others we look at. Okay, and so at the end of next week, I will have some discussion with you as to which of the additional data sets we look at. I'll tell you something more about them. Right, so this week, 2 people have sent me information about possible data sets. I would like this week everyone else to send me their proposed data set so I can make sure you have a suitable data set for your report. Now, because, one question is that before next week, I want you all to tell me whether you're all going to continue to do remote Zoom. If everybody's going to do remote Zoom, then I will not come into the laboratory and I will choose somewhere without the background noise. But that means if you come into the laboratory, you will have to run Zoom on the screen. So I will assume everybody is doing remote Zoom unless you tell me otherwise. So unless I get a message from someone by email this week before Friday, I will assume that next Saturday I will be either at home or in my office where I can control the sound environment. Okay? So if anybody needs me to be in the lab. So I mean, in fact, if at the last moment you come to lab, that's okay. You can still come in using your student card. It just means I won't be here and you will need to have the Zoom window open on your desktop together with the JMP window, okay? Now, because you guys are running the trial version of JMP, I'm assuming, that means that the license only lasts 4 weeks. So I will try and see whether I can get, so I talked to SAS, who owns JMP, and they had previously told me they were at least in principle willing to give me a slightly extended license for you that would last for at least another month. The other possibility is that when it comes to your report, you come in and use the JMP version in the laboratory, which you have access to based on the email the grad school sent you. The other possibility, of course, is you simply install the trial version using a different computer with a different email account. Okay? And again, you don't have to use JMP for the report. I personally think it's by far the easiest, but if for your thesis you're using Stata or R or SPSS, those are all fine with me. I don't mind. It's just that obviously that's not what we're doing in the sessions, okay? So if anybody needs help with a JMP license extension, please send me an email and I will see. I'm trying to remember what exactly the SAS person told me. I think she told me I would be able to download a new 1-month license. So in other words, you would basically get a 1-month extension. So I will try and see what I can work out before the final session. Now, because of the holiday, we're not having our 4th session in the 4th week, but we're having it in the 5th week, right? Because May the 1st is a public holiday, it's Labor Day. So next week we have the class on the 24th, but our final class is on May the 8th, by which time the trial licenses will have expired. So I will try and see whether I can get the license extension sorted out for you. If I can, I will put that in the Google Drive folder. Okay? Any questions before we finish for today? Okay, then thank you all very much. And I will put the recording in the Google Drive folder. Okay? Thank you all very much.
Thank you.